panelists. Please welcome Steve Collins and Arko to the Hackaday Super Conference stage.
Thank you very much. Thank you. So I guess we have our bios covered, so let's just start going. And I press that to go forward. Okay. Yeah. Do you want to come up here and you can gesticulate over there while I gesticulate over here? So what we're going to talk about today is a project that R and I worked on for the last couple of years called Cobalt, which is a technology demonstration of some new planetary landing technology. And let's see, I'll talk about most of this stuff as we go forward. Whoop, too fast. Okay, here we go. So where are we today in terms of landing technology? This is a picture of the surface of Mars near the Curiosity landing site, which is in the middle of a big crater here. And what you see drawn there is the Curiosity landing target ellipse and landing target ellipses for a bunch of earlier missions. And you can see we started out in 1976 with the Viking lander with a much larger error ellipse there for us to land. And that's because the Viking lander basically was not guided. We basically delivered the spacecraft to the top of the atmosphere, and it used a heat shield to go down through the atmosphere and then put out a parachute and fired some rockets at the end and landed where it was going to land. But it didn't make any measurements of where it was at. It was pretty much an unguided thing dropping in through the atmosphere. And when we did Viking, we didn't know diddly squat about Mars's atmosphere. And over time, as we've done these other missions, we've learned more about Mars' atmosphere, and so we can do that a little bit better with Pathfinder and then Spirit and Opportunity. But those all basically use that same dump it into the atmosphere and let it go where it's going to go. For Curiosity, the landing ellipse got a lot smaller, and that was because we introduced guided entry. And in guided entry, what we do is at the top of the atmosphere, we tell the spacecraft where it's at, its position and velocity. And then the spacecraft has an inertial navigation system on it that tries to keep track of where the spacecraft is as it flies down through the atmosphere, slowing down. And at the end, it uses a parachute and some rockets to set the spacecraft down. The guidance part of guided entry is the fact that for Curiosity, we put a little offset in the spacecraft so that as the heat shield flies through the atmosphere, it flies at an angle, and we can roll that the spacecraft around the velocity vector to make the lift that creates either point up or point down. And that allows us to control how far downrange the spacecraft goes. And so we use the inertial navigation to estimate where we think we're going to land, and we use that guidance algorithm, which is basically stolen from the Apollo program, to control how far downrange we go. And that gave us enough control that we can shrink the landing ellipse from basically these Spirit and Opportunity size things to the Curiosity size. For Mars 2020, which is the next generation Mars lander that we're working on now, if you come to JPL, you'll see it being built in the high bay there. We're adding another level of technology, which takes pictures as we're coming down on the parachute, compares those pictures to a map that it has on board, and then just before we touch down, it can make one little correction. It can divert a kilometer, a few hundred meters. And what that allows us to do is it doesn't actually shrink the landing ellipse any, but it allows us to put the landing ellipse someplace where there might be some hazards that are inside the ellipse, like there's a cliff or there's a mountain in there. And that little divert maneuver lets us designate an area, and the terrain relative navigation system takes pictures, figures out where it is on the map, and says at the very last minute, you're about to land on a big pile of rocks, so divert 300 meters to the left and land someplace that's not so dangerous. let me just back up and say one more thing for context here. For the Curiosity landing, you'll see that we landed out here on the flat lake bed sediments in the bottom of this crater. But the interesting stuff is here on Mount Sharp, which is in the center of the crater there. Geologists always want to land in terrifying, dangerous places, because that is the place where the interesting geology is. That's where uplift has happened. There's a cliff. There's a river has carved a canyon through the rock. So they always want to land right next to the cliff or right next to the mountain. For Curiosity, we landed out here in the parking lot, and then it took us 2 years to drive to the mountain. So if we can land in more dangerous places, then we can do more science because we can get started on it earlier. And this lander vision system technology will help us to do that on Mars 2020. Going forward, we want to land in even scarier places. We want to land on Europa, and where the surface is very unknown. We're not sure what the frozen ice that's cryogenic. We don't know what the surface properties of that are. On Earth, you have GPS. You have a thick atmosphere, and the parachute can slow you down to slow enough that you can actually survive a landing. But on Mars, there's no GPS at present.
Yet.
The atmosphere, yeah. I mean, someday, maybe, right? If we send a lot of stuff to Mars, we're going to want to have a capability like GPS there. Mars also has this very thin atmosphere, and a parachute will only slow you down to a few hundred miles an hour, which is too fast to land. So you have to worry about rockets and stuff for the final landing. All of that is true on Europa, except it's an unknown surface, high radiation environment, and other spooky things. So let's see. Why do we? Oh, that's because those things, and here we go. So what do we do going forward to make our navigation better, be able to land in scarier, more terrifying places? Well, the technology that Cobalt is exploring is to have an inertial navigation system, like Curiosity did, have a lander vision system that does terrain localization, like Mars 2020 is going to, and for Cobalt, we've added a LiDAR, which lets us measure the altitude of the vehicle above the surface, and actually how fast the vehicle is moving across the surface as additional navigation measurements. And the LiDAR is actually a Doppler LiDAR, so not only does it tell you I'm this distance from the surface, it actually, if you're sliding across the surface at a constant altitude, it can measure the velocity that you're doing that. And that lets you actually measure something where right now we're kind of doing with inertial navigation alone. Another thing on the, basically we're integrating IMU, a camera that takes these pictures that let us do this localization. You can see from an earlier technology development program that was part of building LVS, you can see pictures of the desert there, and there's little green landmarks that have been picked out of the image, and they've been found on this onboard map to let us localize. And like I said, for Cobalt, we're going to add this LiDAR. Let's see, and that's an arrow. And then here's what our payload looks like for this. This is the Cobalt payload. Those three things are LiDAR beams. There's a camera, and there's an IMU underneath Elvis there. Elvis became the logo for us because if you say the LVS acronym really fast to yourself 5 or 6 times, you start saying Elvis, and so somebody thought that would be a cute logo. You can see it has a compute element, camera, LiDAR, and that little is packaged in a little cylinder like that, and you'll see when we look at the rocket how that fits in. So here's the flight payload. Once again, you can see the compute element, the LiDAR, and the IM. Wait a minute. Isn't that your Hackaday badge, Arko?
It is. So on Friday when I actually got this badge, I was looking at it, I'm like, it has a camera and an IMU, and sure, it's missing a gyroscope, but that's like 2/3 of our payload. And I'm like, man, if I had a LiDAR, and I remembered, I'm like, I bought one of these off of SparkFun, and it speaks I2C, and there's I2C ports on here, so I integrated that on there and turned it into a very overpriced measuring tape. So you could actually point the camera at the thing you want to measure. There's a little crosshair and then a little readout of how far away that object is. But with enough time and code, you could probably implement Cobalt on here.
Perhaps someday we'll attempt it. So here's what we got to do, which was crazy, amazing, fun thing, right? I usually work flight projects, which are kind of at arm's length. I'm in a control room somewhere, and all the rocket stuff happens on the other side of the country. But we got to fly our payload, which you see up at the top there, on this rocket, which is built by a company called Marsden, that has a liquid oxygen and IPA, isopropyl alcohol, powered rocket that'll fly up to 1 kilometer and go 100 miles an hour sideways and stuff like that. And so if you want to put together a Kickstarter and pay them to go fly your experiment on their rocket, I'm sure they'd love to talk with you. But NASA has a program that pays for flight opportunities with companies like that and things on helicopters and balloons and stuff. And Cobalt got to fly on this crazy rocket thing that Marsden operates. Let's see, is there anything else to say about that? So here's the flight profile. We take off from a concrete launch pad out near the Mojave Airport and turn on our various sensors as we go up. And it peaks out on the flights that we did at 500 meters. And then throttles down and starts descending. And after descending for a while, it pitches over and starts gaining some horizontal velocity, trying to sort of mimic the thing that we would do if we were going to land on Mars and carry our camera and our LiDAR and stuff through a representative profile. And then, we straighten up and land on another landing pad a few hundred meters downrange. And the Marsden folks that operate the rocket said when we went out there, they said, now, when we throttle down, it's going to be scary because, you'll hear the rocket take off and it's making a whole lot of noise, and suddenly it's going to get very quiet, and you'll think the engine has shut off, and you'll see it descending back toward the ground, and you'll be sure that you're going to crash. And indeed, that was right. It was very spooky.
Yeah, very terrifying.
And you is it going to start back up? Is it going to throttle back up? What's going to happen? So during the whole descent phase, it's crazy town. But it was super fun to go out there and work with the Marsden folks. They have a different level of comfort with risk than the folks at KSC do. And that was, it was really a rewarding collaboration with them. Here's a little bit more stuff, details of our payload, the IMU and the LiDAR and stuff. One of the things that we have to do, like Curiosity had to initialize the inertial navigation system at the top of the atmosphere, we have to, before we take off, initialize our inertial navigation system. And we did that with a machine vision thing where we put some targets out here. Arko spent many long hours slaving away in the desert, measuring to the millimeter where all these targets were so that we can take a picture of them before we launch and do some image processing on them and figure out the orientation of the vehicle before we start. So I'm going to set the next slide, and I'll let Arko start talking.
Cool. You want places?
Yeah, if you want. That way you can click when you...
Awesome. Thanks. So system architecture, this is kind of a high-level block diagram of Cobalt. So starting on the left side, you have GSC or ground support equipment. That's kind of just an external power supply we use for testing. The rest of this is the payload. So we had a power condo that had batteries, a battery monitoring system, a bunch of power harnessing that supplied power to our three main subsystems, the compute element, our lander vision system, and then the LiDAR. So the lander vision system consisted of a camera and an IMU. The NDL, the navigation Doppler LiDAR, the LiDAR itself has a telescope and then a bunch of, an electronics box with the actual lasers and sensors and whatnot, and that provides us velocity and position. So all that information is fed into our computer. So one note here, this is going to be important in a few slides. This little bar over here represents a backplane. So all these various cards actually slide in and connect to this connector, kind of like like a motherboard with a PCI. We used a standard called compact PCI, where there's nothing compact about it, as you'll learn really soon. So these boards, it's like a single board computer that kind of does a bunch of housekeeping. It's like an i7 processor, off-the-shelf stuff. An FPGA, which handles all the sensor information coming in. And does all the synchronization and all that fun stuff, and then hands it on to a Leon, which is, I believe, a RISC-based architecture processor that does all the Steve's magical math that I can't even understand. And it comes out with a beautiful state estimation of where the rocket is.
Do you want to say anything about the radio?
Oh, right, yeah, and then we have a little radio. We're in a trailer like a mile away, listening and initializing and talking to our payload. So we get a little bit of information. It's not really great bandwidth, but enough to kind of set it, start it, check that everything's good before it takes off, and then once it's flying, it just dumps out information, doesn't listen to us until it's touched down.
And it's Wi-Fi, right?
It is Wi-Fi. I didn't want to mention that.
Oh, sorry about that.
It's in the publication, so
yeah.
Yes. Thankfully, we're not flying this thing anymore, so don't go out there and start trying to hack it. So all in all,
we could barely get it to work. So
we had trouble talking to it.
With
so.
a directional antenna and stuff like that.
It was a major pain. I did a bunch of link budget analysis to even get that thing to work. There's a whole talk I could write about that.
But talk about the rocket.
Yeah, let's talk about the rocket. Put together, we have this silver piece here is the compute element. We built a custom computer chassis, essentially. The white box here is the NDL electronics, and then you have the power condo. It's really hard to see. You see a bunch of terminal blocks at top. But it's made up of a bunch of decks that have various like battery monitoring systems and batteries and stuff like that. And then an EMI shield that surrounds it so we don't interfere with the vehicle and the vehicle doesn't interfere with us. So we bolted on top of their rocket. They have their avionics, we have our avionics, we do a bunch of checkouts. And one note here, the rocket is gimbaled, and you'll see that in the video that we play at the end here.
Really the only interface between, there's a mechanical interface between the rocket and our payload, but there's like one serial line. It's super minimal interaction between our payload and their rocket thing.
Yeah, essentially you don't want to kill your driver. They're flying us. So one really big thing at JPL is testing. We spend a short amount of time designing and building, but we spend a lot of time testing and iterating and testing and iterating. That's really our secret sauce. So the four big tests we kind of put together that we're going to mention today are the swing and bump test. That's mainly for synchronizing our sensors. I'll get into that in a few slides. The PIP test, that is the targeting system that Steve mentioned earlier. That's kind of to initialize our payload. And then the ATV and Zodiac test, which is kind of like a full test, and I'll explain that in a few slides. So you have a newly built LiDAR by Langley Research that's been integrated into your payload, and you have your lander vision system that was developed at JPL. And now you got to kind of mesh these two sensors together, and knowing the phasing between these sensors is very, very important. When the sensor measurement is taken and when it's being processed. So we thought, well, we could put this giant payload on a crane and then swing it around, and the laser beams would see the ground get closer and then further and closer and further and make a nice little sine wave, right? And appropriately so, the IMU would also see a rotation rate that's in a nice little sine wave. And we figured, okay, well, if you can line up these, you could, if you plot them, you could actually see the phasing difference between these sensors, and now you know what the timing delays are between them. So we took it to a high bay, and we swung this giant, expensive payload around, and it didn't give us quite the resolution, you know, like we'd do a few time steps here and there, and you really couldn't tell, like, is that really aligned, is it not aligned? And what we really needed was like an impulse function, right? Like a direct time step, a step function to go into this. And it turns out this 99-cent piece of foam did the trick.
Payload. Is that a simulation?
Yes.
Oh yeah. This is what we.
The audio cuts very, very fortunately, because it starts with me saying stupid payload as I'm bashing this thing into it, and it's, you know, this is what we call testing. So what's happening here is the beam A, the beam in front, is actually looking at the surface here, and as you're dragging this piece of foam across, you see a velocity, right? As soon as it bashes into the cart, it comes to a stop, so velocity is high, then suddenly drops to 0. Meanwhile, the IMU is happy and dandy, and suddenly it goes, blah, something smacked into me, and now you can actually get a nice little step function to compare your phasing. So it turns out 99-cent piece of foam, way better than an expensive crane and swinging it around.
It took us a little bit of consideration before we're like, is it okay if we just bash on the side of this thing? Because, you know, flight hardware people are like, you know, you can't bash on the side of my thing. And we're like, well, it's not as bad as the rocket on the trailer going out across the bumps out to the launch site, right? So if it can't handle this, it's not going to survive transport to the launch pad.
And we actually had done a bunch of vibe analysis too, so there's that's a whole nother talk there. Pip, we're gonna have to skip through this a bit because we don't have a whole lot of time. We had a bunch of these circle dots. We set up. We took the sensor assembly actually off and put it on a tripod and got it to roughly the geometry we think we would see or we would have at the pad to test out the system as close as to flight as we could.
Don't tell anybody, but this stuff in the back is for like a comet landing experiments and stuff.
Oh yeah.
But we're not supposed to talk about it.
Yeah. Gonna skip through these slides. So we ran into some issues in alignment and total station issues. We'll come back to that if we have time later. So earlier I mentioned this CPCI backplane, right, that I really hate. And these next two slides are actually just me wanting to rant about how much I hate CPCI. So we had seated all the cards together, and you know, Steve started. I'm like, here you go. It's all good for you. Have fun. And he'd be working on it, and you know, a few weeks have gone by, and then suddenly he's like, you know, this FPGA is not programming anymore. It's completely random. And I'm like, random? That's not a good thing, is it? So I tried to look at it. We thought it was a power. Maybe things are glitching here and there. We could not figure it out. And it was truly random. Like there was, you know, the temperature could be different, the alignment of the planets could be different or the same, and it didn't make a difference. And it turns out the tolerances on our custom-made chassis were just wrong enough that these cards that slide in and are actually a blind mate, we couldn't tell if they had made a proper contact until we took it apart and realized, oh, geez, the card wasn't seated right. So you just push it in a little more, and suddenly your problem's gone away.
So this is basically the guts of our computer,
Yeah, right.
with the cards not plugged into the connectors like they're supposed to be because there's, you know, small alignment tolerances and stuff. Packaging for space stuff. Packaging is a huge deal, right? To reliably package stuff so that connectors that are designed to be put together and taken apart stay
density.
together through environments is a challenge.
Right, and so earlier I mentioned, you know, it's a blind mate, right? You put the card in, you don't know how well it's seated. We seated the card the first time actually, and suddenly our current our overcurrent protection kicked off and went, oh, no, I'm not turning things on. I'm like, what the heck could be the problem? Like we checked it out, buzzed a few things out. We're like, I can't figure this out. Pulled the card out and then looked at the pins. We're like, what could it possibly be? This stupid one single pin bent and shorted against VIO, which is our voltage for the logic. And so the logic rail was faulting, and thankfully it didn't cook any hardware, but I hate you, CPCI. So at this point, we've done initialization testing. We've synchronized everything. We're good to go. But now we want to get as close as we can to doing a full systems test. Okay.
Yeah.
A full systems test. How can we at JPL test this stuff out so when we get up to Maston and suddenly have 20, 30 people burning money, you don't want to sit there trying to debug a problem that could have been solved back at home. So we put the payload on a Polaris that was actually left over from our DARPA robotics challenge, bolted it on, built a little box using some Digilant parts, like a Zinc processor. It's a nice little ARM FPGA board to simulate the same exact timing and voltage characteristics as the rocket. So this box pretends to be the rocket, and as far as Cobalt knows, it's moving. The IMU and the LiDAR is seeing data being excited, or the data is being excited, and it's talking to a box that looks to it exactly like the vehicle.
So this is where all of Ara's hacking stuff comes into play, because he's building these little boards and writing software for them and reading the GPS and logging all of that data, and it's all stuff that you folks are familiar with.
Yeah. Not a whole lot of crazy stuff in there. So the next step was, well, we want to initialize the payload with this targeting system and then take off and drive around just like we would be if we were on the pad about to take off into the sky. So we tried to get the geometry right, but the distance was just not right. Earlier we had it on a tripod and the geometry was working.
The rocket's a lot taller than the ATV.
Way taller than the ATV. And so we jacked up the ATV and that didn't work. And it turns out right next to this railing here down the street was literally a street. So we put our pip targets, you can't see it here, down on the ground, and then we would park the vehicle here. We could see down to the street where the targets are, initialize the system, and then take off and drive around the lab, come back, and the video you're about to see here is us actually returning from our trip. Hoping not to smack the payload into the side of the other vehicles. This was terrifying to drive, by the way. And then we tried to park it back where we started to kind of close the loop and see what our errors were, essentially. And we looked really badass doing it.
We made great little plots of us driving around JPL and overlaid them on the JPL map and to see if this payload was navigating.
Yeah. And quick shout out, we did use Raspberry Pis to actually monitor our battery system. We even had a mechanical keyboard with a panic button appropriately on the escape key. Thought I'd throw that in there. You guys might appreciate it.
He named it Watney.
I did. So before Masson lets us do a free flight where we go up into the sky and come back down, we have to do 3 tethered tests, and this is kind of like a shakeout, right? We think we're ready, they think they're ready. We've plugged into one another, and now it's like, okay, we're talking, everything's good, but is it really going to work out when we go to light the engine? So what we did first was a tethered test where we put the rocket on a crane and essentially do a short hover. So we initialize our system, look at the targets, take off, hover a couple meters above the ground, move to the left, move to the right, do a full flight duration of a minute and a half or whatever it was, and then come back to center and plop down. So the first one, you kind of shake out the issues. The second one, you think you've solved them, and usually you have, and there's only one, like this one error that you didn't, quite solve, and you fix that, and you do the third one. Everything is good to go, and once you've done that, we can do...
You get to go fly.
Woo! You get to go fly.
Hopefully you get YouTube to show us flying.
Yeah. Come on, man. Let's see if this works.
You want to...
Whoa, what's going on? What? Oh, it's a delay.
Copy that. Okay, moving to the engine start page. Cobalt, this is LC. Go, no, go for flight. Pilot, activate locks and IPA pre-valves.
Activating locks and IPA pre. Locks and IPA pre are active.
Those are the Maston
Activate
guys.
locks and IPA press valves.
Activating locks and IPA press. IPA press and locks active.
Pilot, prime engine.
Priming engine.
Okay, team, here we go. Maston off to all, 6-second countdown. 6, 5, 4, 3, 2, 1, ignition.
That's the part where you're like, oh, this is going to go bad. That's Mojave Airport in the back.
I'm getting packets.
The rocket engine does a number on the concrete pad.
Oh yeah, it's also really beautiful. It's like creme brulee concrete.
It's literally melted into glass.
Yeah.
Right, right under the nozzle.
And we got some beautiful NASA sent out for some photographers, and we got beautiful pictures out of these things. You can see a nice plume and the rocket flying around. The important thing here to mention is the team. Steve and I are up here, two guys, but really it wasn't just us. It wasn't any one person. It took a big team to make this happen. In fact, there's people missing from this photo because we had shifts between Langley Research and Johnson Space Center and even JPL working out who's going to be here to support. And so this is to the team. Really made it happen. Awesome people to work with.
We're in our NASA trailer off, basically at the horizon.
Yeah, so
there.
in the video you saw us in a trailer. We were way off in the distance there.
In this amazing, ancient, dusty NASA van.
Should have put a slide in there
Oh,
for that.
it would have been, yeah.
That was quite beautiful. Yep. And I think that's it.
So, Sam, we have a couple minutes for questions, and then we'll answer more out there. Anybody? Yeah.
Were you using the LiDAR for mapping or just ranging?
It was basically ranging, but also probably more important for measuring the velocity. It's a direct measure. Since it's a Doppler LiDAR, it can directly measure the 3-axis velocity of the vehicle, which you can use to update the inertial navigation.
Oh, that's a really good question. So this has actually moved on to Johnson Space Center. There's a project called Splice that's hoping to take this technology and actually miniaturize it, like less than half the size of what we had now, and cut down on the mass, make the LiDAR better. So it's moving on. On top of that, it's kind of branched off. So there's, help improve the technology, add more LiDARs, try different sensors, build a platform where you can actually integrate different sensors, maybe a flash LiDAR, what have you. And then another branch of it is going into the flight world. So we learned a few lessons from this that are actually going directly to help the Mars 2020 mission with its lander vision system. Hopefully this technology will fly on Mars in about 3 years.
One last question, back there in the blue.
So as part of the miniaturization, is that going to be shifting to radiation target processors? You mentioned you have a Core i7 in there. What are you looking to replace those?
Right. So the i7 was mostly for housekeeping and configuring the FPGA and the Leon. So the Leon is closer to there are like radiation hardened copies of that chip available. We love using the RAD 750. That's a PowerPC processor that's radiation hardened. And in fact, the flight computer that Mars 2020 is going to have is going to be using an FPGA and a RAD 750. So. That be doing no, I believe that's done on the FPGA.
The FPGA, the image processing all gets done on an FPGA, and then for Mars 2020, the RAD 750, moves the data around, does a minimal amount of math, but most of the heavy lifting of the, image processing stuff and feature extraction and stuff like that gets done on the FPGA. Cool, thanks. If you have more questions, we'll be out here in the foyer.